So, hello everyone, welcome to the TCS seminar at Jagiellonian. Our guest today is Mathieu from the University of Warsaw, and before he did his PhD in École Normale Supérieure de Paris, and he is going to tell us about the 2+ε approximation for the maximum independent set of rectangles.
Thank you. So I'm happy to be here, and thank you for the invitation. It's also a pleasure to give a live talk instead of a talk alone in my room talking to my computer. Feel free to interrupt me and ask questions. I will try to have some kind of interactive talk. That would be great. So I want to share with you some new results about the maximum independent set problem of rectangles. So recently there have been some movement, say because there was some nice result by Joe Mitchell, and we with my co-authors we worked on his paper and we tried to improve his methods, and we came out with a good understanding of his techniques. And I want in this talk to present to you this new technique, and I hope you will get some flavor of it. So the problem is the maximum independent set of rectangles. So it's a particular case of the maximum independent set problem. Okay, so given a graph, we are looking for a set of vertices such that no two vertices in this set are adjacent. Okay, and the goal is, of course, to find an independent set of maximum size. Okay, so it's a very classical problem, and it's known to be NPR. In terms of approximation, because we are interested in approximation in this talk, so it's very easy to get an approximation. So approximation with factor n, which is just you pick one vertex. Okay. And actually, we cannot do much better in general, because there is this result by Ashstad that showed that it's NPR to get better than n to the 1 minus epsilon approximation. So basically, on general graphs, we cannot do much. So if we want to prove some good approximation algorithm, we need to restrict ourselves of some subclasses of graphs. And one interesting class of type of instance is the graphs that comes from geometric intersection graphs. So you can imagine that you have a set of objects, and each of these objects corresponds to a node in your graph, and you have an edge if two objects intersect. Okay. So, for example, you can have the interval graphs, which is the intersection graphs of intervals of a given line. For example, this is the interval graph of this set of intervals. You can have unit disk graphs, for instance, which is the graphs obtained by the intersection of unit disks. Okay. Super. Dziękuję.
Not better.
No.
Don't know what to do with this.
Usually, I don't put a lot on the right, top right. So
Screen sharing is on.
How did I do it?
Sorry. Okay, so it actually also makes sense to look at the independent set problem on this special type of graphs, because we are just looking for objects that are independent from each other, family of non-overlapping objects. Okay, one application for COVID maybe is that imagine you have this, you are running office and you have to decide which of your workers are going to go to work and you want to maintain this distance of security. You can imagine that it's one guy on a desk, and basically they have to have 1.5 meters around them, otherwise they might infect each other. So you have to find the best set of independent sets in this unit disk graphs, and you want to maximize the number of persons that can come to work without infecting each other. Okay. Now that you know that there are some nice applications, I can continue. So today, oh, it's not working.
Maybe you need to.
On. It was on.
Maybe you need to get the focus because Bartek changed how it works.
The light is working, but I feel it's not connected.
Try now. Okay, it works.
Okay, thank you. Sure. So the focus on this talk is the independent set problem in the set of rectangles. Okay, so we have a set of rectangles, and we can look at the associated intersection graphs. And the goal is to set independent set, or equivalently a set of non-overlapping rectangles. And we want to maximize the number of such rectangles. Yeah. So this restriction is still NPR. Okay. For this type of hardness result, you can imagine that you can actually model like planar SAT by using some kind of path of odd length formed by rectangles. I mean, it's kind of general techniques to see that this type of problem remains NPR. Okay, anyway, and so let me show you a brief history about this problem. So first, maybe I didn't mention, but for many type of intersection graphs, the approximation is well understood. For instance, for the intervals, we have polynomial time algorithm. For squares and spheres and unit disks and even pseudo disk, which is kind of generalization of disk, we have pitas. So the only kind of simple shaped case for which the approximation is not really well understood is the case of the rectangles. So the story started by a log n approximation. So we talked about it today. It was just cutting a line separating two instances, and then either we find an independent set on the line, which is a kind of interval graph instance, or we have the union of the two solutions, and by arranging everything, it gives a log n approximation. Then there was a log n approximation for the problem. There is this, it's not polynomial time algorithm anymore, but a quasi-polynomial time. And it's a pita, so it's a 1 plus epsilon approximation, but in time n to the polylog n. And this actually shows that a pitas is expected for the problem. It cannot be APX hard unless some well-believed assumption of theory is disproved. So we expect a pitas for the problem of rectangles, but at this time, not even a constant approximation is known. And because I'm here, I want to mention also the extension by Bartosz and Parinia Sharansu. This log n approximation, but for the weighted case now. Okay, the weighted case, I mean each rectangle comes with a weight, and we want to maximize the weight of the solution, so the sum of the weights of the rectangles. Okay. And recently there was this breakthrough result by Mitchell that showed 10 approximation for the problem, and this was the start of our project, was to understand this new technique and develop his idea and extend it as much as we could. And what we obtained is 2 plus epsilon approximation. And as I will show you later, it's kind of a natural bound for this type of techniques. So our techniques follow the same idea as Mitchell, actually. So I'm sorry if you know already the paper of Mitchell, you will probably not learn a lot of things today, but I want at least to reformulate his ideas and to present it in a different manner. So even if you know it, you still can get something from this talk. So the general framework is that it's not so previous results. There was usually based on the linear program and are using different type of techniques. Here it's fully combinatorial, and it's based on dynamic programming. So the goal is to show the existence of a good structured solution. So a special family of independent sets that have some nice structural properties. These nice structural properties will allow us to compute the best structured solution by dynamic programming. Okay. So our goal is mostly to show that among these good structured solutions, there exists among these structured solutions there is at least one good, for which the ratio with the maximum independent set is small. Okay. So that's the challenge, to kind of have something that is structured enough so that we can compute it, but not too structured so that we can prove that it's actually possible to find something of good size. Okay. So I will maybe not explain all the details of the 2+ε approximation, but maybe I can show a 6 approximation. Actually, it doesn't matter so much what is the constants. If you understand what I'm going to present, you will kind of understand how to trick everything so that you can change what is the constant. Actually, in the project, we had many different stages where we improved we had 2 different 6 approximation on 2 kind of different techniques, then 4, then we had 3, then we had 2+ε. So it doesn't matter so much. It's the same idea. Okay. So as a warm-up, let's solve the maximum weight independent set for interval graphs. So for intervals in a line. Yes.
So I have a question. So what was the main ingredient that allowed you to jump from 10 to 6 or below? Is there something that Mitchell did not notice, or?
I think not anything amazing. I would say that if Mitchell would have spent more time on his 10 approximation, he would have improved it to 6 or to 4 or even to 2+ε maybe. Mm-hmm. It's just that it's difficult to put everything together to make it work. When you look at the detail, it's kind of complicated and it's difficult to come out with something that is working. And but I can answer your question later. Why we jump from 10 to 6 and what is the intuition? Mm-hmm. Okay. So one way of solving this problem is to try a divide and conquer. So we can cut somewhere. We solve recursively in both sides, and then we combine the solution. And we can try, of course, we have to get rid of all the ones that are intersected, okay? And maybe we can try different cuts and hope that one of these cuts will give us the optimal solution. And actually, this is how we can obtain an optimal solution, a maximum independent set on this maximum weight, even an independent set on this for this problem. This can be turned into a dynamic program. So you can imagine that each cell of your dynamic program corresponds to some interval of the sub-interval, and the value of this cell is the maximum weight independent set of the intervals lying inside. And when you want to compute the value of one cell, you try all the cuts and you look at the sum of the 2 values, and this is your. So kind of here, all the intervals, they are well structured because there exists a cut that for which the optimal solution can be cut into it. Just like you just have to cut between two intervals of the optimal solution. Okay, let's try to generalize this idea to rectangles. So here we would cut in 2 dimensions with a vertical cut like this, or maybe horizontal. So what happens if we do that? Here we cut, and we have to get rid of this this rectangle, and this rectangle. So on the right we obtain only one rectangle, so we don't have to continue. On the left we still have a lot of rectangles, so we can continue. Maybe we will do that cut. So we will lose this other rectangle, and then this one we can subdivide in 2. And here we obtain a kind of subdivision into 4 rectangles. So these cuts that are cutting the pieces in 2 each time, let's call it a guillotine cut. Okay. And let's say that a set of objects, so a rectangle in the plane, is guillotine separable if there is a sequence of guillotine cuts that separates each object into a different piece. So for example, the set formed by these 4 rectangles is guillotine separable. Okay, this is the sequence of cuts, guillotine. And this is an example of what could be well structured. Okay, because we will see later that this can be computed by a dynamic program. I mean the optimal solution. So of course, not all set of rectangles is guillotine separable. For example, this one, whatever the first cut that you do, you have to cut somehow. Okay. And you guess it, we can compute by dynamic program the optimal guillotine separable independent set, meaning the independent set that satisfies this guillotine separable property with maximum size. This is possible to do it by dynamic programming. So more precisely, what is the dynamic program? For each cell, you specify now a rectangle inside our bounding box. Okay, and the value is the inside is the value of the best guillotine separable instance inside. Okay, and when we want to compute the values of our cells, we start by small rectangular areas, and we split our current cell into 2, and we try every possible cut, and we make the sum of the values. Okay. So we can compute by dynamic programming the optimal guillotine separable independent sets. Now the question would be, what is the? Can we now analyze this? What is the best optimal guillotine separable independent set compared to the optimal independent sets? So what is this ratio? There is a conjecture by Pack and Tardos that this ratio is actually bounded by a constant. There are some stronger conjecture that say that maybe this constant is 2. But the fact is that this is still a conjecture, and we don't really know how to prove it.
So
I mean, we don't
have it to approximation, yes?
Sorry?
If it's true, we have it to approximation, correct?
If it's true, then if this stronger conjecture is true, that gives a 2 approximation. Okay. And it would also, I think, improve. I think it would give a constant approximation even in the weighted case, because here the conjecture is about that we can that is working with weight also.
Okay.
Okay, so for now, so that would be of course a very interesting direction, and it's also for some respect of more mathematical, it's an interesting conjecture by itself. but we'll do something kind of more complicated. We will not just do guillotine cuts, we'll do some more complicated cuts. So what is the idea here is that what other types of structured solution we can explore. So we can, let me define a PC cut as, imagine I have a polygon with C sides, okay? For example, here 6, and P refers to the number of segments of my cut. No, sorry. P is the number of is the number of pieces in which I cut my piece. Okay. So, for instance, here guillotine cut. This is 4 and this is 2 because I cut in 2 and I use only rectangles. Maybe I consider more complicated piece and I consider cutting it like this. And then I would still have two pieces, but they would have each maybe 6 sides. Here, maybe I want to cut in 5 parts, and all of them are rectangles. Okay, so we can imagine a more general definition of a well-structured independent set. That would be the PC separable independent set. If we can find a sequence of PC cuts that separates all the rectangles of the instance without cutting any of these rectangles. Okay. Yes.
So why in this last example we have 12?
So 12 here refers to the number of edges of the pieces. Okay.
Okay.
C is the complexity of a piece, which is kind of the number of edges. Why complexity? Because in the dynamic program, because the goal is to have these facts. That
okay, so
actually
it doesn't relate to the number of like cuts we have in our.
So P is the number of cut, kind of number of pieces that you will obtain at the end. And in red, it's the complexity of each piece. You want to maintain the fact that the complexity is bounded. So the fact is that the optimal PC separable independent set can be found in time n to the big O of P times C using dynamic program. And it's the same dynamic program.
So okay. Just to make sure, I just want to make sure that my polygon has at most C sides. And
yes.
The pieces that I cut into also have at most C sides.
Yes.
Okay.
All the pieces that you consider, they all the time have C sides.
Mm-hmm.
And the reason is that this will be all the pieces that you will consider in your dynamic program. Okay. So now we have kind of more freedom. Okay, we have a general family of what is well structured, and our goal is just to identify some value P and C for which we can prove something about the size of the optimal PC separable independent sets. Okay, so that's I want to show that if we take P equals 3 and we take 26 sides, then I can show that the ratio between the best of these guys and the maximum independent set is at most 6.
So what were the constants by Mitchell?
It was 10, but it was not exactly the same program. So it has also this dynamic program, but this dynamic program has to remember some kind of other things.
Uh-huh.
It was not really these geometrical problems,
okay.
But it was roughly the same type. Mitchell was using also this type of pieces, but they had more constraints. They were called the corner clips, that they correspond to some
26 is scary, right? He had less than 26. Maybe he had other conditions, but like.
So the fact is that you can reduce actually this 26 to say 18.
Uh-huh.
And there are two things, is that when you decrease the number of edges, you actually increase the length of the proof. So
okay.
Our goal was also, because in Mitchell's paper, the analysis of these partitioning arguments, it takes like enumeration of 60 or 70 different cases. And we found that maybe it would be good to simplify the analysis. And actually, in the 6 approximation that we have in our paper, there is only one case of the analysis. If we would actually reduce to 18, maybe that would make more cases. But we took the choice to don't care so much about the number of edges, and to have a proof that is easier to check and to. But it's an interesting question actually. Like, what is the smallest P and C, so that we maintain some kind of certain approximation.
Well, that's the conjecture. What is about, right?
So the conjecture is really about. Yeah, okay, but it's not clear. Like even I don't know what is the ratio in this case. What can we prove? It's not clear. I don't know. There must be some interesting question. Or in this case, I don't know. Okay, and the fact is that the full theorem is that that's why maybe explain this epsilon is that if we use roughly one of the epsilon sides, we can get 2 plus epsilon approximation. The number of pieces is not so important actually. 2 or 3, it's roughly the same. Actually, even if we have more than 2, we can still cut one by one and kind of. So this first parameter is not important, but the second one is kind of important.
So I guess if you allow big O in the second, it doesn't matter what you put in the first, as long as it's at least 2, right?
Yes, you could put 1 over epsilon and. Okay, so I want to give more details to dive now into this. So why how to prove this type of approximation? So the analysis is roughly is based on Mitchell's ideas, and it's just making them simpler and more efficient. So first, what we do is to assume that. So we will start by a maximum independent set, and we will construct from this set. We will remove some of the rectangles, and we will prove that one subset of the maximum independent set is well structured. Okay, is 326 guillotine separable, 326 separable. Okay. So our job will be to work on this set that is opt. So imagine that is the optimal solution, the maximum independent set, and we will build our solution and control how much do we lose each time. So one first assumption is that we will take the rectangle in opt, and we will make them maximum. We will push their side in every direction. So basically, we will make something like this. So we push them in the bounding box of the instance. Okay. And I claim that this we can do it without loss of generality, because when we will make our cuts, everything that cuts the big rectangles, they will cut also everything that cut the small rectangles, they would cut also the big rectangles. So if we are able to extract a good subset of this maximal set of rectangles, we can do it on this one. Okay.
The larger one. Yeah.
So we will work on this one.
Yes.
Okay, and this will make things easier. Okay, let's get some intuition and let's try to I don't know, cut somewhere. So imagine we cut there on the sides. Then we don't do any progress. No, we just lose some rectangles. We will not be able to prove anything. So intuitively, the best cuts, they are not close to the boundary. They are somewhere in the middle. So formally, to say that, we will protect the boundary rectangles. So the rectangles that have a side on the boundary. We will protect them by these fences that are just some horizontal line segments that intersect no rectangles and kind of protect the rectangles that are on the sides. Okay. And one rule that we will use is when we will cut is to never cut through a fence. That's one strategy that I want to apply. Okay, never cut through a fence. So somehow it means cut in the middle. So of course, I will not use straight cuts because we know it's still open the conjecture and we don't know what to do. So we will have some bends in our cuts. So one restriction that we make is that the horizontal segments of our cuts, they will not intersect any rectangle. So for instance, this second cut, it violates that rule because this part is cutting this rectangle. And this we don't want. What we want is something like this, that cuts in the middle and for which only the vertical parts, they may intersect some rectangle. The horizontal parts, we will not cut anyone. Okay, so that's my two kind of rules that I want to maintain while doing my cutting, recursive cutting. Okay, so let's see what I can obtain by doing this. So maybe I will cut in the middle like this. So what happened is that now after cutting, so I have to get rid of these rectangles. And I will recurse, okay, on the right and on the left side until I have one rectangle per piece. You remember? But now, if I focus, say, on the right piece, I have new boundary rectangles. Okay, so I have to create new fences. So I will create new fences on the right and on the left. And again, I will apply the same rules on this piece on the right and on the left. So say I cut straight again like this. So I have again on these four pieces, I have new new fences, new boundary rectangles. Okay, let's concentrate on one piece. So now we cannot cut by guillotine cut, vertical cut, without intersecting a fence, right? We have to cut necessarily one fence. So what we will do in this turn is to use some bends in our cut. So here we will make this cut, okay? So it will create some new piece. Here we will maybe use this cut, and then, okay, and then we can cut like this. So one thing that when we do that, we want to also maintain the complexity of the pieces that we create. We don't want to be we want to be at most constant at any moment. And if we do it many times, maybe we will increase step by step the number of edges. So this is, I guess, a polygon with 26 edges. So it's not so horrible. We will assume one invariant that this piece that we consider, they are actually horizontally convex. So horizontally convex, it means if you take 2 points at the same y coordinates, the segment lies inside the piece. Okay. And it turns out that we can additionally maintain this property, which makes the proof easier to analyze. Okay, but it's not important. So let me describe precisely what is the partition rule that we will apply to get our good, to prove that there is a good structured solution. So we will look at our basically horizontal one piece of our partitioning, and we have the left edges and the right edges. So one of these two sides contain a lot of edges, unless we can do any cuts, and that's fine. On the left side, we will partition into the top, the bottom, and the middle part. Then we will take the longest fence from the middle, so maybe it's this one, And then we will cut along this fence, okay? And then we will cut on the top and on the bottom until we hit some rectangle that is protected by a fence. So if it's protected, for instance, by a fence on the right, we can do a small turn like this and then join the boundary. Maybe we will hit a rectangle that is protected by a fence on the left, then we can circumvent this rectangle and join the boundary again. And this will form a cut into three pieces, this one, and this one, okay? And you can notice that it also maintains the fact that the pieces are horizontally convex. And by choosing carefully the size of these groups and stuff, we can maintain that the number of edges is at most 26 for all the pieces. Okay, nothing very... Okay, so that's basically the idea, is to define this partitioning. Now we want to...
So wait, so you choose somehow three vertical sides on the left, say.
Yes.
Somehow, yeah. And then you, as you described, you throw in the horizontal segment stemming from all three of them. And then by your, and that's it, by your description, you put it into three. Okay.
And by this invariant that we maintain, we can claim that there is only this part of the cut that may intersect rectangles. Here we can intersect some rectangles, it's okay, but we don't want to intersect some rectangles that are protected by the fence. So this is actually the important fact that we will use in the analysis, that in our cuts there is only one vertical segment that may intersect some rectangles of the optimal solution.
So there are lots of border cases, like I don't know if there are only two sides or stuff like this.
Yes, yes.
Yes.
So the intuition is that if there's a small number of sides, then it doesn't matter so much what you will make a simple cut with only one. I mean, you can cut from anywhere, and it will maintain the complexity of the piece.
So all you keep as an invariant besides the 26 is that it's horizontally convex. You don't anything else. You don't keep. That's it for the invariant. I can come up with any shape I like, and you will process it.
Yes.
Okay. Okay.
It must be connected. So it means you don't want to have a right edge and a left edge that are intersecting. But this is okay because you would create two pieces.
It does. Okay. Okay.
But to give me any shape, I can tell you how to partition, and that I guarantee that if you do that, it will give 6 approximations. So the important fact is that we have only one vertical part of the cut that may intersect some rectangles. So now, how do we, if we apply these rules of cutting, how do I prove that at the end I obtain a set of rectangles that is at most 1/6 of the original set of rectangles? That's my goal. Okay. So imagine that's my first cut. Okay, it's a legal cut. I have to cut some rectangles. I lose some rectangles. So I want to, for each rectangle that is lost, I want to pay this loss by charging some rectangles around. And I want to make sure that this rectangle that receive some kind of proof of payment, they will be part of the final solution. Okay. So for each rectangle that is, say, killed by a cut, intersected by a cut, I will look around on the right and on the left, and I will charge this rectangle. You can imagine that each time a rectangle is intersected, is killed, you take one coin that you might share, and you split this coin into other rectangles. And at the end, you want to make sure that every guy that survived doesn't have too many coins. Okay, basically that's the intuition this saving charging scheme. So here, the fact is that when we do that, we will make this in a way that each rectangle that is charged at most 4 times. And that, so it will make sure that at the end, a rectangle is not overcharged. And this will prove what we want.
So it doesn't get charged anymore in the future. That's what you want to say?
You could charge. Basically, the intuition is that if this guy is charged later in the future, it will be charged by the right side. And then it will be kind of, it will not be charged anymore. So I will show later in more details how we do this charging if you want. But basically, when we charge someone, we identify one of its corners. And we make sure that we charge a corner, and a corner is charged only once. That's kind of the strategy. Okay. It's not so easy to do it exactly, but that's the idea why there is this 4 times, because we charge a corner.
The fact that these rectangles become those that you charged, that they are the new boundary rectangles, means that there are those fences, so you will never again cut them.
Exactly.
Yeah. Okay.
That's the goal of the fences, is to actually protect the rectangle that receives charge. That's why we also say protected, because when a rectangle will be a boundary rectangle at some point, it will be protected and it will never be intersected. So it will be part of the final solution. So it's kind of safe to charge the rectangle that are boundary rectangles. The problem, okay, it's a nice idea, but the problem is that not every rectangle can be can charge. I mean, it's possible that a lot of rectangles charge the same rectangle. Like if maybe I want to make a drawing. Imagine I have a rectangle like this, and I have some. I have a lot of rectangles like that. Yes, and that this one, and we cut here. Then all this rectangle, they will like to charge this one. Yes, so that's a problem. So we cannot, the point is that we cannot do this charging process for all the rectangles. So we need to differentiate a different type of groups, the one that we will be able to charge and the one that we cannot. So I define the one that are nested horizontally. Nested horizontally means that their right or left edge is contained in the right or left edge of another rectangle. So basically, that are the one that we don't want to pay for, because otherwise our charging scheme doesn't work. And the one we have also the one we can define the one that are nested vertically. Okay, so bottom or top side contained in another vertical or horizontal side of another rectangle. And the fact is that a rectangle cannot be both horizontally and vertically nested. Imagine that if it's the case, then these two rectangles must intersect, and you assume that they are an independent set. So the fact is that if you look at your instance of opt, they are either nested horizontally, nested vertically, or none of them. So, you know, without love of generality, you can assume that at most half of them are nested horizontally. Otherwise, if it's not the case, you just flip your instance. Okay. So there are rectangles that we cannot pay for, but it's okay because they represent only half of the population, of the total of opt. So we don't give. We can lose all of them. We don't care. What is important is that we can pay for at least a constant fraction of the sets. And that's what we are doing. We are only charging the ones that are not horizontally nested. Okay. And for this, we can actually claim that we can find someone, we can find some corner to charge. And this corner will not be charged by anyone else. Okay, then we can make a kind of analysis, and that gives some constant factor, but it doesn't matter so much. So how the factor will vary, it's basically how much rectangle do we charge. We can decide to charge only on one side, or we can decide to make a fractional charge, share it on one side and on the other side. We can decide to charge only one rectangle or several rectangles. Making all these kind of choices will kind of slightly change the approximation. So for instance, the 10 approximation of Mitchell was that we lose a factor 2 because we lose all the red rectangles. And then we show that, and Mitchell shows that for each rectangle that is intersected, what was the thing? Is that 4 rectangles that are intersected may charge the same rectangle. So basically, we can save only 1/5 of the blue rectangles. So we lose 2 and then we lose 5. When we do our 6th approximation, we showed that the blue actually, they only charge 2. So only 2 rectangles that are intersected can charge the same rectangle. So we lose only a factor 3, then 2, so it gives 6. On the 4 approximation that we had, it was every rectangle is charging another rectangle. So we lose only half of them, of the blue. Okay, I hope this slightly answers your question about how we go from 10 to 6.
So in all the strategies, you give up half at the start.
Sorry?
So in all the strategies, you give up half at the start.
Yes, exactly. That's why also I said that this is 2 is in some sense a natural barrier of this. So some takeaway of this technique is that if you want to find a good solution, you can try to look for a good structured solution. The strategy of fences and cutting and this charging argument and this nested that is kind of, maybe we cannot charge everyone, but we will make sure that at least a constant fraction can be charged. Okay, now, so in the remaining, I can give you either more details about what is this thing, because I haven't really described how it works. If you want, I can give you more details. I can also give more details about the 2+ε approximation. I don't know in terms of times where we are, and, if you have still energy.
So we have plenty of time.
We still have plenty of time?
Yes.
Okay.
I don't know. I would see more details of the 6, but I don't know about you guys.
I'm okay to see more details of the 6.
I have also a lot of open questions, and maybe we can spend more time on this section as you prefer. Okay.
Because there are also online participants, and I would like to see 1/epsilon, so this 2+ε. So yeah.
Okay, so I will try to cover a bit of everything. Maybe that's the compliment. Okay, so these are parts of some other slides. So I gathered different slides from my co-authors. I'm sorry, there's a mix of style and also approximation ratios. So this we know, this we know. Okay. One remark is that this notion of nested is exactly the same as in Mitchell's paper. He also defined this notion of nested. And one improvement that allowed us to kind of reach this 2+ε is a new definition of being nested. The fact is that with this first definition of nested, we can reach 3, but not more than 3. So the difference between these two definitions is that I consider that, okay, now this guy is nested on the right if it's either contained in the inside of another edge, or maybe the inside plus the top left corner, but not if it's contained in the, not if it's at the same level down. The reason is that actually here I say that I cannot charge them, but maybe I can just decide to pay for the lowest one, and the rest of them I don't pay for them. But I can still save one guy in this, and that's the goal of this definition. Kind of allow that in this group of people that we sacrifice, we don't sacrifice all of them, we will save one of them. And the fact is that we still have this notion that we cannot be at the same time nested. So now it would be nested on the right and nested on the bottom. We cannot be both nested on the top and in the bottom. So we still have these two groups. We can still, without loss of generality, remove the smallest one. And the consequences here is that now we can actually only charge on one side, but it's not so problematic. So there are a lot of changes that enters, but it's still kind of working. So precisely, how do we identify a rectangle to charge? So we will say that R can charge for R prime if it sees R prime. But, more precisely, if it sees its bottom left corner, we will all the time charge the bottom left corner of the rectangle. Okay. So for instance, R, it sees R prime 1, but it doesn't see R prime because kind of R prime 1 is blocking. It also sees R prime 2, so it could charge R prime 2 if you want. But like R prime 2, we don't want to charge. R prime 2 is actually nested, so we cannot. So it does not see R prime prime. And this is how we will charge. We will charge someone that we see, okay? And we will make sure by some geometric arguments that it's clear that only one rectangle can see R1, yes? So that's why we don't charge too much the same rectangle. So basically that's the idea, more precise how to charge, who to charge. Okay, that's.
The rectangle can see a number of other, right?
Yes, and in that case, you can decide who you want to charge.
Arbitrarily.
Yes, yes. Okay. Because in the difficult case, you see only one person, only one rectangle. So there is this lemma, but I don't want really to prove it, that either a rectangle sees someone or is nested on the right. So can charge someone or doesn't have to be charged. Okay, that's the message. But I don't really want to prove this, but it's work. And this is an example, like if you want to see an example, imagine this is our current cell. And in white, this is like the empty space. And we cut like this. So these are the rectangles that are intersected, okay? So R1 charge R prime 1, okay? Then R2 charges R prime, also R, okay? This is a problem with the label. because it sees its bottom left corner. R3 charges R prime 3. R4, we want to charge R prime 3 also. So there's a problem in our charging scheme. But actually, no, because this guy is nested. So we don't have to pay for it. Okay. We already paid for it. And R5 is charging this rate. So the fence, you know. And also the fact is that now when we are charged, there is a direct line from one of our points to the boundary. So we became protected by a line fence. So when we receive some payment from someone, when we receive some tokens, when we are charged, we are protected. We will not be intersected later, and we will be part of the final source. Okay, that's some formal statements, but it's not interesting. So how to improve to, what are the ideas to improve to 2+ε? So basically, if we want to improve the approximation ratio, when we intersect someone, we want to charge more rectangles. And in particular, here we want to charge 1/epsilon rectangles. So for each rectangle that is intersected, we will charge 1/epsilon rectangle. That will be protected and that will never be intersected. So if we want them to never be intersected, we also need to use longer fence. So fences with length 1/epsilon. And because we use longer fence and we will cut through the fence, we need more sides also. Okay, so let's use tau as the length of the fences. So basically, we will use some fences like this that are monotone and that uses tau bands. Okay, and we will take tau as 1/epsilon. I mean, some constant. There is some big constant there, but it's not important. Okay, so this is an example. So this is my set of in gray, the set of rectangle of the optimal solution. In yellow, this is like the cut that we are making. We are still making sure that only one vertical part of the cut may intersect some rectangles. Okay. And imagine that these are the rectangles that are intersected. So we need to pay for these rectangles. For instance, the process now. Okay, first I need to mention that to this set of rectangles, any set of maximal rectangles, we can associate this kind of tree structure that you see here. So there is an arc, there is a directed edge between one rectangle to another one. If the first rectangle sees the second rectangle, okay? So for instance, this rectangle sees this one. This one sees this one. Now it's possible to see several rectangles, okay, on the right. So we always see someone on the right. There are some rectangles that doesn't see anyone. These are the ones that are nested. So the one in red, there are leaves of this this forest. And we will use this structure to devise our changing argument. So the argument is that we will follow when we have to charge someone. When we have someone intersected, we will look at one vertex after. So one rectangle, we will charge this rectangle. And then we will continue. We will charge this rectangle. And then again, and then again. Okay. And each of them we will distribute one token until we have distributed 1/epsilon tokens. When we receive a token, we will not be intersected later because we will be protected. But maybe at some point we fall into someone, like in that case, that is a leaf, is nested, doesn't have anyone to continue. So then we charge this guy, okay? But the fact is that when we charge a rectangle that is nested, it's kind of good because we assumed already that this guy was removed from the instance. So in some sense, it's lucky to charge a rectangle that is already removed because we already paid for some removal. And
so sorry, the way how I understand it is that normally a rectangle has a charge 1 because it pays for itself.
Yes.
And then it can receive an epsilon charge in this scheme.
Yes.
Right, which is distributed among many rectangles.
Yes.
But a red one has initial charge 0 because it does not pay for itself, and then you can put a full charge on it.
Yes.
And it will be like still 1.
Yes.
Okay, good.
So that's the trick. Either we can follow a long enough path and we distribute a lot of charge along all that path, or we find someone that is closed and that is already removed, that is red. And then we will actually save this guy, and because we assume that it was removed, that this is good. So that's the process. Either we charge 1/epsilon rectangles that are not nested, or we charge 1 rectangle that is nested. Do you want me to do it again?
No.
Okay, and so to protect then this rectangle, we need to use fences like this that have 1/epsilon bends. Okay. Okay, this is the analysis that is giving 2+epsilon approximation. It's not so interesting. I guess you see it. No? So that's the kind of, now that's the lemma to say how to partition, because I still didn't say how to partition. Okay, I don't want to enter into the details, but now we don't need to assume anymore that the polygon is orthogonally, horizontally convex. And we actually show that our, okay, what we want to, the only important fact is that there is only one vertical lines of the cut that may intersect some rectangle. That's the only kind of thing that we use in the proof. So that's what we want to maintain when we do our cut, that there is only one vertical cuts that may intersect some rectangles. Also, obviously, the number of edges, the number of components. So the proof is really complicated. I mean, it's really technical, and there's a lot of kind of cases like this. There's a lot of sites. Basically, it's still the same idea of partitioning the left side into a central part and looking at the longer fence. But the problem is that now the left side is not well defined, and there is a lot of complication with this proof. And we believe that it's an interesting fact by itself, and it could be used to devise some kind of similar algorithm, geometric algorithm, using some kind of complicated polygons, complicated DP like this. This is kind of general statement, and that was also one of our goals, to have some kind of, there is not even a notion of, yeah, there is a rectangle here. This is kind of almost completely independent from rectangles. Okay. Do you have a question about the 2+epsilon approximation? Do you get at least the ideas to how to go from 6 to 2+epsilon? So, okay, can we beat 2+epsilon? So there is this notion that we have to sacrifice the red rectangles, and we have to assume that it can be sometimes half of the rectangles. So, and it's really not clear how to do otherwise than sacrificing these rectangles. one thing is that there's different ways of defining this set of red rectangles by considering, for instance, the different symmetries of the instance. And we can hope that one of these different symmetries will give rise to kind of a small set to sacrifice. But actually, but on the only instance that we know where all of these kind of possibilities to define this set, they are all like half of them. They are very symmetrical, this kind of out cases. And it turns out that on these out cases, our algorithm actually gives pitas, 1+ε approximation. But at the same time, we don't know how to kind of, there is something missing to improve the approximation. I don't know if it's clear what I'm saying, but okay, the fact is that we don't know how to bit to and also the reason why it's not clear how to bit 2 is that there isn't actually a special case, which is the case where rectangles, they have dimension 1, length 1 on one of the dimensions. So either they are like this or like this. So you can imagine that they are horizontal or vertical lines. Okay. So imagine that the restriction of the maximum independent set problems in this set, in this setting. The fact is that there is an easy 2 approximation for this problem, right?
And they don't overlap like horizontally, right?
They overlap horizontally.
Well, they do.
They do. It's important because otherwise you have a bipartite graph. And the problem is. So it's kind of interesting because, as you said, if they only intersect like vertical to horizontal, we have bipartite graph, and it's easy to solve maximum independent sets. But at the same way, if you have only horizontal or only vertical, it's an instance of interval graphs. So it's also easy, but for a different reason. So this kind of instance combines these 2 cases, and it's NPR, but we don't know. So there is this 2 approximation that consists of looking only at the horizontal or only at the vertical. In that case, we have a disjoint union of interval graphs, yes, and we can compute the optimal solution. So we can just output the best of these 2 solutions, and this is a 2 approximation. But we don't know how to improve. Nobody knows better than this. So that's one, and it seems that it's not so.
There are lower bounds.
What do you mean, lower bounds? It's NPR, I guess. That's the. Yes, because actually the Q-pitas applies for this case too. So there's a Q-pitas for this one.
Oh yes, okay. So you expect it to be.
So you expect a pitas actually for this. Okay, so that's one first question. There was this question at the beginning about the guillotine cuts. So can we actually obtain a constant approximation using the simple dynamic program of with the guillotine cuts? We can imagine some generalization of variants, like instead of rectangles, what if we have this polygon with 6 sides, like the L's? Okay. Then it's not clear that our techniques could generalize to this. What about 3 dimensions rectangles? I don't know what to say. There is also the case of arbitrary line segments. So now instead of 2 directions, they can have arbitrary directions. Then the best bound, the best upper bound is n to the epsilon. The best algorithm gives this. So it would, even finding a polylog approximation for this case would be an improvement. I don't know what is the best lower bound for this case, but so we can also, I don't know, consider hollow rectangles that are just so now if one rectangle is included in the other one, they doesn't intersect. They just intersect if the boundary intersects. But the fact is that this is more general than the weighted case, because you can kind of encode the weights by kind of a lot of them putting together. So actually, what about the weighted case? So it doesn't work, our techniques for the weighted case. The reason is kind of when we intersect someone, imagine this guy has a very huge weight. Even if we can find some people around to pay for him, it might be that the weight of these guys is small, and then we kind of lose control of what's happening. So it's not clear what to do. So the best approximation is by Bartosz, and correct me if I'm wrong, but so you showed that the coloring number is bounded by omega times log omega, big O, where omega is the maximum click. And then, okay, it's not really LP rounding, but you take you compute the optimal fractional solution, and then you build an instance from this optimal fractional solution, and then you apply the coloring now on this instance, and then you take the best color class or something like this. Okay, the fact is that the conjecture is that maybe this is linear, and that would imply a constant approximation for the weighted case of the maximum independent set, and also I guess imply one thing that is interesting is also the gap of the linear relaxation of the click constraint LP, and it's conjecture to be constant also, but we still don't know. So this is another conjecture. Maybe a simple step for the weighted case would be the case where the weight corresponds to the area of the rectangles. My feeling is that maybe this is something that is feasible and easier than, and that we could use some kind of geometric observation to deal with this case. But I don't know. So that's the end.